Hello friend, today we are looking at the DC transient, and basically we are going to look at the mathematical derivations of the different formulas in the DC or direct current transient. We have to note this, that when a DC voltage is applied to a capacitor C and a resistor R connected in series, there is a short period of time immediately after the voltage is connected, during which the current flowing in the circuit and voltages across C and R are changing. So across that point where we are having these parameters, like for example voltage and current changing, we have to say that during that period we can refer to it as the transient period. Similarly, when a DC voltage is connected to a circuit having inductance R connected in series with resistor or resistance R, there is a short period of time immediately after the voltage is connected, during which the current flowing in the circuit and the voltages across inductor R and resistor R are changing. These changing values are called transients. And since we are dealing with the direct current, then we shall call them DC transients. Let us immediately go to the resistor capacitor series DC circuit. So we have a capacitor connected in series with a resistor, and with the switch we have also a battery source. So now this is the voltage VC across the capacitor, voltage VR across the resistor, and V is the total voltage. Now we want to consider that at the instant when the switch is closed, we have to note that by Kirchhoff's voltage law, the total voltage V from the battery will therefore equal to VR, the PD or the voltage drop across the resistor R plus the voltage across the capacitor. So VR is equal to IR according to Ohm's law, and VC is equal to Q out of C. We have to note that for a capacitor, charge changes with time. Therefore, it means if we are to implement that charge changes with time, we can reorganize that formula of VC equal to Q out of C, so that it becomes CVC equal to Q. So when we differentiate, for us to get current here, we have to differentiate charge, because a changing charge with time results into current. Therefore, d by dt of CVC is equal to dq of dt. So meaning that if we differentiate, therefore, we shall find ourselves with the dq dt, which is equal to I. Therefore, the VC by dt is equal to I, which is the current across the capacitor divided by the capacitance of the capacitor. So when we want to get the total voltage VC across the capacitor, it will be equal to 1 over the capacitance of the capacitor times the integral of current with respect to time. Now, having understood that, we can also say at any time or any instant, it means VC is equal to I mean 1 out of capacitance integral of I of t dt, because current is changing with time, and therefore we are giving it as a function of time. So substituting for VR and VC from the equation of V equal to VR plus VC, it gives us that V is equal to, this is VR, which is I of t times R, plus 1 out of C integral of I of t dt. So it means for us to remove the integral sign, we have to differentiate this function, the whole of this function, with respect to time. So when we differentiate an integral, of course we get the opposite of that, so that when we differentiate it, we come back to that function. Therefore, we have to differentiate both sides. dv dt is equal to the d of I of t by dt times r plus 1 over c times d by dt of the integral of I dt. We shall find out that because this voltage source of a DC is constant, therefore the V by dt is equal to 0 because that V is not changing with the time. Therefore 0 will equal to R di dt plus 1 out of C times the current, because when we differentiate an integral we get the derivative of that particular value or function that we are differentiating. It means if we differentiate this integral of I dt, we shall get back to I. So this means 0 is equal to R di dt plus 1 over C I. And if we transfer it to the other side, we realize that the I dt is equal to negative 1 out of RC times I. So when you see a derivative and you want a function, then it means you have to integrate both sides so that we have that function. So if we are to get the I, we have to integrate the I and all the contents that contain I with respect to I, and also the other side with respect to time. So when we rearrange, we correct the like terms together, we find that you have 1 over I di equal to negative 1 over RC dt. So integrating 1 out of I with respect to I gives us the natural logarithm of I. It will therefore equal to negative t divided by RC plus the constant of integration. So meaning that if we are to ignore this natural logarithm, I will equal to exponential of negative t divided by RC plus k, meaning that I is equal to negative t out of RC times. If we are to use indices and powers, we find that this is the same base with the powers being added. It means I can create a similar base. I power it to this particular constant, I multiply it by this, so that we have E exponential of negative t out of RC times exponential of k. So what does this mean? It means that this kind of derivative itself, I mean this exponential of k is a constant because it is exponential of a constant, which is also equal to a constant, say k1. Now that means our I will equal to k1 exponential of negative t out of RC. So when we look at the boundary conditions or the initial conditions, we find out that at time t equal to 0, at the instant when we are closing the switch, sometimes we can even use at t equal to negative 0. It means I will be I naught equaling to k 1 times. If we power this function, if t is 0, then it will be 0 out of RC, so it will be e to exponential of 0, which will give you 1. So if it is equal to 1, then it means k1 will equal to I naught, which is the current of the circuit at t equal to 0. So I of t, when we are to substitute in this particular function, will therefore equal to I naught, which is the value of k, which is a constant, times exponential of negative t out of RC. So RC is equal to a time constant tau. If we are to say time RC, we call it tau, then it is a time constant, and it is the measure of the rate at which a transient shifts to the steady state value, and therefore when we substitute it in our expression for I of t, it will equal to I naught exponential of negative t divided by tau. The analysis shows that at t equal to, as t approaches infinity after a very long period of time, it means I of infinity will equal to I naught times 0, because this exponential of a very big value will tend to 0. Therefore, I at infinity will give you 0, and it will show you that after a very long period of time, the current flowing through this circuit will actually tend to be 0. After a very long period of time, the capacitor creates an open circuit. That's why we are saying that at t equal to infinity, the capacitor creates an open circuit. Open circuit as a result of a capacitor. So we have to note that one is very important, and that this equation shows you a decay of current through this circuit that has a resistor and a capacitor. So look at when values of current are plotted against time, we realize that this is actually our I naught that we are talking about, which is a constant, and the current keeps on decaying as time goes or approaches to infinity. We realize that this I will equal to V out of R, which is the source voltage divided by the resistor exponential of negative t tau. Now, if we are to proceed, let us look for voltage across the resistor in RC DC circuit. Now, from that equation, I equal to V out of R exponential of negative t divided by tau. It means voltage across the resistor VR is equal to IR, and this is equal to I, which is given above, times R. Okay, so this will be V out of R exponential of negative t out of tau times R, and therefore VR is equal to V exponential of negative t divided by tau. So when we plot values of VR values, when we plot values of VR or voltage across the resistor against time, we find that the voltage will decay exponentially from the maximum VR, which is equal to IR, and goes to 0 as time approaches infinity or after a very long period of time. There is therefore an exponential voltage decay across the resistor. What about voltage across the capacitor? Voltage across the capacitor, from the formula V is equal to VR plus VC, it means VC is equal to V minus VR. When we look at the making VC the subject of the formula, we already know V, we already know VR, so we substitute in the value for VR, and it is V exponential of negative t divided by tau, and VC will therefore equal to V into 1 minus exponential of negative t divided by tau. Or we can use the fact that from V is equal to 1 out of C integral of I dt, we can say that I is therefore equal to V divided by R exponential of negative t RC or tau. We can substitute in there and integrate that value. So when we integrate that value of I, the integral V is equal to 1 out of C integral V over R exponential of negative t out of RC dt will give you negative V exponential of negative t divided by R plus K, which is the constant of integration. So now it means if we are to use boundary conditions at t equal to 0, VC or the voltage across the capacitor is 0 because the capacitor has not yet charged at that instant. It therefore means if we are to substitute in this equation star, 0 is equal to negative V exponential of 0, because at t is equal to 0 this whole thing becomes 0. So exponential of 0 we know it is as 1, then plus K. It means this value K, the constant K, is V. So substituting in, it means VC will therefore equal to V into 1 minus exponential of negative t divided by RC. Now, when we look at the graph plotted, we see that there is an exponential growth of voltage across the capacitor. So that's why we see that the voltage across the capacitor grows up to a constant VC equivalent to the voltage source, and therefore we can say this is a capacitor charging, and we see that the graph shows us the voltage growth across a capacitor. Thank you so much. See you in the next video.